Hello everyone. In this section, we are going to discuss protocol layers and service models. Before we are trying to organize our talk on internet architecture, let's take a look for a human daily life analogy. Actually, we deal with complex systems all the time in our everyday life. Imagine if someone asks you to describe, for example, the airline system, how would you find the structure to describe this complex system that has ticketing agents, baggage checkers, gate personnels, pilots, airplanes, air traffic controls, and worldwide for routing airplanes? One way to describe the system might be to describe the series of actions that we take or other takes for us. When we fly on an airplane, we buy our ticket, check our bags, and go to the gate and eventually get loaded on boarded to the plane. In the plane, when the plane takes off and is routed to the destination, after our plane lands, we get off the plane at the gate and claim our bags. If the trip was bad, we can complain about the flight to the ticket agent, getting nothing for our effort. This scenario is described in the following figure. Already, we can see some analogies here with computer networks. We are being shipped from one source to destination using airplane. A packet is transmitted or shipped from source host to destination host in the internet. But this is not quite the analogy we are looking for. We are looking for some structure that we see in this figure. If we look at this figure, we know that there is a ticketing function at each end. There is also a baggage function for already ticketed passengers and a gate function for already ticketed and already baggage checked passengers. For passengers who have made it through the gate, that is passenger who has already ticket and baggage claim through the gate, there is a takeoff and landing function. While in flight, there is an airplane routing function. This suggests that we can look at the functionality in the previous figure in a horizontal manner as shown in this figure. This figure has divided the airline or airplane functionality into layers, providing a framework in which we can discuss airplane travel. Note that each layer combined with the layers below it implements some functionality, some service at the ticketing layer and below. Airline counter to airline counter transfer of a person is accomplished. At the baggage layer and below, baggage check to baggage claim transfer of a person back and bags is accomplished. Note that the baggage layer provides this service only to an already ticketed person. At the gate layer, departure gate to arrival gate transfer of a person and bags is accomplished. At the takeoff or landing layer, runway to runway transfer of people and their bags is accomplished. Each layer provides its service by 1. Performing certain actions within that layer. For example, at the gate, loading at the gate layer, loading and unloading people from an airplane, and by 2. Using the services of the layer directly below it. For example, in the gate layer, using the runway to runway passenger transfer service of the takeoff and landing layer. A layered architecture allows us to discuss a well-defined specific part of a large and complex system. This simplification itself is considered a value by providing modularity, making it much easier to change the implementation of the service provided by the layer. As long as the layer provides the same service to the layer above it and use the same services from layer below it, the remainder of the system remain unchanged when a layer's implementation is changed. Note that changing the implementation of a service is very different from changing the service itself. For example, if the get functions were changed, for example, to have people board and disembark by height, the remainder of the airline system would remain unchanged since the gate layer still provides the same function. For example, loading and unloading people. It simply implements that function in different manner that the change. For large and complex systems that are constantly being updated, the ability to change the implementation of a service without affecting other components of the system is another important advantage of the layering models. But why layering? So this important approach to design and discussing a complex system, as we mentioned. Let's now turn our attention to network protocol. To provide structure to design of network protocol, network designers organize protocols and network hardware and software that implement the protocol in layers. Each protocol belongs to one of the layers. Just as each function in the airline architecture in the previous figure belong to a layer, we are again interested in the services that layer offers to the layer above, so-called service model of a layer. Just as in the case of our airline, for example, each layer provides its service by first performing a certain action within that layer, and second, by using the services of the layer directly below it. For example, the services provided by layer N may include uh, reliable delivery of messages from one edge of the network to the other edge. This might be implemented by using an unreliable edge-to-edge or end-to-end message delivery service of layer n-1 and adding layer n functionality to detect and retransmit lost messages. When taken together, the protocols of the various layers are called the protocol stack. The Internet Protocol stack consists of 5 layers: the physical layer, the link, networks, transport, and application. As shown in this figure, we can examine that the syllabus of this course is roughly organized using this internet protocol stack layers. We take a top-down approach, first covering the application layer and then proceeding downwards. Here we can see that a protocol layer can be implemented in software, in hardware, or in a combination of these two components. Application layer, for example, here we can see HTTP or SMTP. HTTP is the application that we use to browse website, web pages, and SMTP are used for sending email. These two application layer protocol, are almost always implemented in software in the end systems. So are the transport layer protocols. Because the physical layer and data link layers are responsible for handling communication over specific layers, in these two layers are typically implemented in a network interface card. For example, the Ethernet and also Wi-Fi interface card associated with a given link connected to the node. The network layer is often a mixed implementation of hardware and software. Also, note that just as the functions in the layered airline architecture were distributed among the various airports and the flight control centers that make up the airline system, so too is a layer N protocol distributed among the N system, packet switches, and other components that make up the networks. That is, there is often a piece of a layer N protocol in each of these network components. Protocol layering has conceptual and structural advantages. As we have seen, layering provides a structured way to discuss system component. This modularity makes it easier to update system component. As I mentioned, there are some researchers and network engineers are opposing this layering system because of several drawbacks. One potential drawback of layering system is that one layer may duplicate lower layer functionality. For example, many protocol stacks provide error recovery on both peer link basis and an end-to-end basis. The second potential drawback is that functionality at one layer may need information, for example, a timestamp value that is present only in another layer. This violates the goal of layer separation. The application layer is where the network application and their application layer protocols reside. The Internet application layer includes many protocols such as the HTTP protocol that I mentioned, which provide us for web document request and transfer. We have also the SMTP, which provide for the transfer of email messages, and FTP, which provides for the transfer of files between tools and system. We'll see that certain network function, such as the translation of human-friendly names for the internet system, like we convert from www.ietf.org to 32-bit network address that we will learn later about the IP address are also done with the help of a specific application layer protocol, namely the DNS or domain name system. We will see later that it is very easy to create and deploy our own new application layer protocol. An application layer protocol is distributed over multiple end systems with the application in one end system using a protocol to exchange packet of information with the application in another end system. We will refer to this packet of information at application layer as the message. In this figure, we denote it with M. So it is the information that is generated by the application layer. Below the application layer protocol, we have the Internet Transport Layer protocol that transport application message between application endpoints. In the Internet, there are two transport protocol, the TCP and UDP. One of these two transport layer protocol can transport application layer message. TCP provides a connection-oriented service to its application. This service includes the guaranteed of delivery of application layer messages to the destination flow control, which is that match the sender or transmitter transmission or receiving speed. TCP also breaks long messages into shorter segments and provide a congestion control mechanism so that a source throttles its transmission rate when the network is congested. So below when application generate message, the transport generate segment, and this segment consists of segments of message that has been divided. And here we can see in transport layer we put a header and we denote it with HT. So HT is the header of this protocol. The Internet network layer is responsible for moving network layer packet known as the datagram. So the datagram is moved by the internet by the network layer protocol from one node to another host or another nodes. The Internet Transport Layer Protocol that we have previously discussed, TCP or the UDP, in the source host spaces a transport layer segment and a destination address to the network layer, just as we would give a postal service on a letter with a destination address. The network layer then provides the service delivering the segment to the transport layer in the destination host. The Internet network layer includes what we call as the IP or the Internet Protocol address or the IP address. IP address which define the fields in the datagram as well as how the end system and router acts on this field. There's only one IP protocol, and all internet components that have a network layer must run the IP protocol. The Internet's network layer also contains routing that determine the routes that datagram take between sources and destination. The internet may have many routing protocols. As we show later, the internet is a network of networks within a networks, And the network administrator can run any routing protocol that he wanted. Although the network layer contains both the IP protocol and numerous routing protocol, it is often simply referred to as the IP layer, reflecting that the IP is the glue that binds the internet together. The internet network layer routes a datagram through a series of routers between the source and destination to move a packet from one node or host or router to the next node in the route. The network layer relies on the services of the link. In particular, at each node, the network layer passes the datagram down to the link layer, which delivers the datagram to the next node along the route. At this node, the link layer passes the datagram up to the network layer, and here we call the network layer message as the datagram, or usually we also call it as the packet. Here we can see also the network layer header encapsulates the previous or the upper layer message. For example, the transport layer gives us the segment, and the segment is further encapsulated with a header from the network layer or the HN, and we have another message that we call as the datagram. The service provided by the link layer depend on the specific link layer protocol that is employed over the link. For example, some link layer protocol provides reliable delivery from transmitting node over one link to receiving node. Recall that this reliable delivery service is different from the reliable delivery service of the TCP from the transport layer, which provide reliable delivery from one end-to-end to another system. Example of link layer protocol includes the Ethernet, Wi-Fi, and the cable access networks for DOCSIS protocol, as datagrams typically need to traverse several links to travel from source to destination. A datagram may be handled by different link layer protocols, a different link along its route. For example, a datagram may be handled by the Ethernet on one link and by the triple P on the next link, or the PPP on the next link. The network layer will receive a different service from each of the different link layer protocols. In this course, we'll refer the link layer packets as the frames, or yes, usually we call it as the frame. So the frame is packet from, or the datagram that encapsulated with a link layer header. While the job of the link layer is to move entire frame from one network element to a neighboring network element, the job of the physical layer is to move the individual bits within the frame from one node to the next node. The protocol in this layer are again link dependent and further depend on the actual transmission medium of the link. For example, if we use the twisted pair copper wire, or UTP or CTP, STP, single mode fiber optics, that is type of physical layer medium. For example, Ethernet may have many physical layer protocols, one for twisted pair copper wire, another for coaxial cable, another for fiber optics, and so on. In each case, a bit is moved across the link in a different way. So this illustration gives us example of how we perform the encapsulation. At the beginning, we have the message generated by the application layer message, application layer protocol, and then the message is further encapsulated or covered with a header from the transport layer, and therefore we have the segment. The segment is further encapsulated by the uh, third layer protocol. It gives the header and give us the datagram, and finally the datagram is further encapsulated by the second link layer, and we have the frame. This is similar to matryoshka dolls or stacking dolls from Russia. Uh, Further, we can see that the physical path that takes down a sending end systems protocol stack up and down the protocol stack of an intervening link layer switch and routers, and then up the protocol stack at the receiving end. A useful analogy here is the sending of an inter-office memo or letter from one corporate branch to another via public postal service. Suppose that Alice, who is in one branch office, wants to send a memo to Bob, who is in another branch office. The memo is similar to the application layer message. Alice puts the memo in an inter-office envelope with Bob's name and department written on the front of the envelope. The inter-office envelope is analogous to the transport layer segment. It contains header information. For example, here in our case, the Bob's name and department number, and encapsulate the application layer message of or the memo. When the sending branch office mailroom receives the inter-office envelope, it puts the inter-office envelope inside another envelope, which is suitable for sending through the public postal service. The sending mailroom also writes the postal address of the sending and receiving branch offices on the postal envelope. Here, the postal envelope is analogous to the datagram. It encapsulates the transport layer segment, which is the inter-office envelope, and which encapsulates the original message of or the memo. The postal service delivery delivers the postal envelope to the receiving branch office mailroom. There, the process of the de-encapsulation is begun. The mailroom extracts the inter-office memo and forwards it to Bob. And finally, Bob opens the envelope and removes the memo. The process of encapsulation can be more complex than we have already described. For example, a larger message may be divided into multiple transport layer segments, which might themselves each be divided into multiple network layer datagrams. And at the receiving end, such a segment must then be reconstructed or reassembled from its constituent datagram. This figure shows us the process of services, layering, and encapsulation for each layer. Each message generated by application will go down to the transport to be a segment and move down to network to be the datagram, and then moving down to the link to be a frame, and then in the physical the message will be transmitted to another physical node from a physical medium. So here we have the message M. Here we use like a smallest doll, and then going down encapsulated by another header with a header from transport layer segment. And we see here that the doll or the message is being covered, and the message is encapsulated, is added with HT, which is the header of the transport layer protocol. Moving down, we cover the doll with another cover, with another encapsulation. Also the segment from the upper layer transport covered with the header of the network to get to be a datagram. This cover or the header is the HN, which is the network layer datagram header. Going down to the next layer, here we have the frame, and we encapsulate the message or with the segment from the network, sorry, the datagram from the network layer, which header of the link layer, or here we denote it with HL. Here we have the frame, and then the frame is further transmitted, and here transmitted to using physical medium, and from the link layer the message is encapsulated using the reverse process. In the link layer we remove the HL, and we get our datagram back here in the network layer. And in the network layer we remove the HN, the header of the network layer, and then we have the segment. And in the transport layer we remove the segment is removed from its header HT, and then we get our original message back in the application layer. So the application in the end host will be able to play or use the message sent by the application from another host. Let me repeat the concept of the encapsulation. So at the sending host, an application layer message M in this figure is passed to the transport layer. In the simplest case, the transport layer takes the message and appends additional information, so-called the transport layer header information, denoted by HT in this figure, that will be used by the receiver side in the transport layer. The application layer message and the transport layer header information together constitute or combine to be a transport layer segment. The transport layer segment is further encapsulates the application layer message. The added information might include information allowing the receiver side transport to deliver the message up to the appropriate application, and use the error detection bits that allow the receiver to determine whether the bits in the message have been changed in the route. Transport layer then passes the segment to the network layer, which adds network layer header information. Here we use HN notation. Such a source and destination in the destination and system addresses, creating a network layer datagram. The datagram is then passed to the link layer, which obviously will add its own link layer header information and create a link layer frame. Therefore, we can see that at each layer, a packet has two types of fields. First, the header field, and then a payload field. The payload is typically a packet from the layer above. As we discussed in this course, routers and link layer switches are both packet switches. Similar to end system, routers and link layer switches organize their networking hardware and software into layers. But routers and link layer switches do not implement all of the layers in the protocol stack. They typically implement only the bottom part of the layers. Shown in this figure, link layer switches implement layers 1 and 2. We add with frame, and then we send through the link layer, and then to the switch, and then during the switch the HL and HN is not removed, and in the router we remove the HL and we add another HN, and we add another HL, and then in the receiver we remove the header from each layer. So here in the figure, link layer switches implement layers 1 and 2, and routers implement layers 1, 2, and 3. This means that, for example, that internet routers are capable of implementing the IP protocol or internet protocol, a layer 3 protocol, while link layer switches are not, since switches use only link and physical layer protocols. We'll see later that while link layer switches do not recognize IP addresses, they are capable of recognizing two addresses, such as Ethernet addresses or MAC addresses, which is embedded to the physical devices. Note that hosts implement all 5 layers. This is consistent with the view that internet architecture puts much of its complexity at the edges of the network, which is the host. In our case, which the end devices, which that may be a computer or a mobile devices. Now let's see an example of a problem. We are developing application that uses TCP IP model, which is the similar model layer that we see in the previous discussion. We use it for data transmission, and our application generates a data segment that are exactly 1000 bytes. So the message is 1000 bytes in size at application layer. As the data moves down to the layers, to the physical layer for transmission, each layer adds its own header. So this is the concept that we use in the encapsulation. Assume that following header sizes for simplicity. So this is some information that we may use in the problem. First, in the application layer, no additional header. For this example, there may be no header, but in reality, some application protocol may add headers. For example, in the each file has its own header. A Word file, a Word document file has its own header. An image file may have its own header as well. And then so it is the fifth layer, and at fourth layer, which is the transport layer protocol or the TCP, it adds 20 bytes. So the header is 20 bytes. The network layer or the IP adds its own 20 bytes as well. Here at the third layer, so here is the message, and here we have the segment, and here we have the datagram. And the link layer Ethernet header has 18 bytes and a trailer of 4 bytes. So totally we have 22 bytes. So here we make it frame. So here is the second layer. The lowest layer, layer 1, which is the physical, the physical layer has no header, because the physical only transmit the information that is given by the data link layer. So calculate the total size of the frame by time it reaches the physical layer transmission, and verify if it exceeds maximum transmission unit. For example, here in the Ethernet networks, the MTU or the maximum transmission unit is 1500 bytes or 1500 bytes. If it does exceed, propose a solution to ensure successful transmission of the data. Here we have the information from the problem. Now let's solve this problem. So the solution is like this. So here the initial data size from the application layer, which is the original message, is 1000 bytes. So by adding transport layer header, the TCP header is 20 bytes. So we have so we add the header, so 1000 bytes with 20 bytes, we have 1020 bytes. So this is the segment size that we obtain. Further, we move down to the network layer header. So here we have the segment. IP header, we have 20 bytes as well, and the new size is 1020 bytes. That includes data and also the header. So here is the segment. The total segment is 1020. In the the network layer, we add another header, 20 bytes from the IP header. So 1020 added with 20 bytes, so we have 1040 bytes. So this is the datagram. Moving down to the data link layer. Here we have two parts that includes the header and also the trailer. Actually, both are considered as the header, because these two are not the original information or not the message itself. So we have 18 and 40 and 4 bytes. Totally from the datagram we have 1040 bytes, and then we add 18 bytes and we have another 14 bytes. So totally we have additional 22 bytes from the link layer. So totally 22 plus 1040 bytes, we have 1062 bytes. So totally, here we have also the frame. And in the physical layer for transmission, totally we must send 1062 bytes. Comparison to the Ethernet MTU or the maximum transmission unit, is 1500 or 1500 bytes, because of the total size of the frame is 1062, which is less than the Ethernet MTU. The data the data frame doesn't exceed the MTU limit and can be transmitted successfully. So fortunately, we don't need to do anything to help the transmission, because the frame size is less than the MTU. So these are the solution. We have the size of the packet for each layer. Okay, thank you very much. This is the end of the discussion of the layering.